Good morning, everyone, and welcome to the Hedera Smart Contracts workshop, which is a part of Oracle Hacks. So thank you all for joining us today this morning. And we have with us Brendan, who handles developer relations at Hedera, and he's going to teach you how to build a smart contract on the Hedera network. So Brendan, how's it going?
Yeah, good, thanks. How about yourself?
Yeah, all good here, Brendan.
Awesome. Okay, yeah, so I'll begin. All right, everyone, welcome to the Hedera Smart Contracts workshop. This is a hands-on workshop, and it will be following a tutorial that I put together recently, and I've shared with you on the hackathon Discord. I'm just going to start sharing my screen, if you'll bear with me for a sec. And let me know if the screen is visible.
Yep, it's all good, Brendan.
Okay, so you can see my screen. Amazing. Okay, so where were we? Yes, so this is the GitHub repo that I shared with you, right? And this gives you some basic instructions in the README, but the main tutorial content is inside the docs folder. So if you click on docs, and then you can go through these in sequence. There's an intro, which you have to do. And then after that, you can choose to do either via Hedera SDK JS or Hardhat. And then, or you can do both, and then you can complete with the outro, right? So that's sort of the sequence that we'll be going through. And we'll be starting off with this one. So for example, the first thing I'll be going through is this. Now, before we start, just so you know, what we will do and what we won't do is for prerequisites, this tutorial requires you to know JavaScript and also some basics about the Hedera network. And I believe in a previous workshop, the previous one given by one of my colleagues, she talked about Hedera network as a whole. So hopefully you've covered that as well. If not, we'll watch the replay. In terms of system prerequisites, you'll need Git, you'll need Node.js. Actually, these two are not really required, they're optional. And then finally, you'll need a POSIX compliant shell, right? And an internet connection, right? All right, and moving on, the other thing that I've asked you to do prior to this workshop is to do the configuration steps, so step B1 through 5. But I'll just go through them briefly as a sort of recap, right? So let's begin, right? So I'm going to start off with the main thing over here. And let's see if I can arrange my windows a little bit. Right, sorry, bear with me for 1 second. All right, ready to begin with the introduction, right? So let's start off with what smart contracts are, right? So I've written about this in the tutorial, but just very briefly, it is a program that executes on the network. In the context of a blockchain or a DLT, right? That means that all of the nodes who are achieving decentralized consensus on transactions, they also need to achieve decentralized consensus on how the smart contract changes over time, right? So each transaction that you send it to, say, invoke a function on a smart contract on this program, it needs to be agreed upon by the network as a whole, and only then will that function call succeed, right? So that's one of the key differences between a smart contract and a sort of regular program, right? The other key difference is that while its state is mutable, so the data that's stored on it can be updated, the code within it is immutable, meaning it cannot change. So that's something that you don't see in Web 2, for example, because whoever owns a particular website or software, they can update the software. Whereas with smart contracts, the code that is deployed is the code forever and you can't change it, right? There are some workarounds for that, but that's beyond the scope of this tutorial, right? Okay, so let's this is a hands-on workshop, as I mentioned earlier on. So let's get started. So the first thing we'll need to do is go to this repo, right? Which you should already have the URL to, and then you'll need to copy the Git repo link, and if you git clone, you'll want the main branch, right? 1 second, and then the repo name, and you can just use that command if you want, but I am going to clone it directly into another repo because I have multiple copies of this, having worked on this earlier on. All right, and go into that directory. So once you've done this, you've got effectively a copy of what's on the repo within GitHub, and that's your starting point. Now, I'll just give you a bit of orientation of how this repo is structured, because that's quite relevant, right? Essentially, where the branches, right? So, yeah, okay, that's right here. So there's a main branch, and that contains the initial state of the repo. And then there is a completed branch, which contains the final state of the repo. So if you, for following along this tutorial, you are strongly encouraged to start with the initial state in the main branch, which is the default that you get when you do a git clone anyway. And then if you want to see what is the fully correct version that you wish to attain at the end of it, then you can skip ahead to completed. And if you kind of want like a bit of a cheat sheet, I've included a link as well. So I'll just open that up over here. You can actually see, you know, what all the changes that you'll need to make are using a git diff as well. So this is like sort of an easy shortcut in case you just want to jump ahead on your own when you're exploring or using this as a reference material. So that's just some sort of housekeeping, but let's move on. Right. So now we've got this project that has been cloned over here, right? And the next thing to do is configuration, right? So let's open this up. All right, so I've got the text. I'm going to increase the size of the text in the terminal so it's easy for you to see. And I've increased the text size here already. Okay, so the first thing is going to be that you have a .env file, right? Excuse me. Right, you've got a .env file, and it contains these 4 environment variable keys that you'll need to set as part of the configuration. Now, these values, you do not want to edit them directly. Instead, what you'll need to do is cp.env.example to .env, right? And that is provided to you as a convenience, and then you want to edit this one, right? So the first thing we want to do is to get an operator account, and this corresponds to step B2 in the tutorial, right? So if you look at your tutorial text, for example, let me see if I've got this open, right? So if you go to introduction and you scroll down, right, you can see step B1, we just did it, and step B2 is creating an operator account, and here are all the steps that you need to do it. So essentially at the end of it, you'll get to the state where you get to Hedera portal and you have an account ID and a private key, and that's what you need to copy into this, right? So I'm just going to copy mine that I prepared earlier on over here. So this is my operator ID that I got from the Hedera portal. And here is my operator account. Hang on, let me just copy that. All right, we're getting there. Then after we've done that, the next thing we need to do is to get a seed phrase. Now, there are multiple ways to get a seed phrase. You can do it via NPM packages, or and if you like a visual way to do it, I would recommend that you go for this website called iancoleman.io/bip39. Right, I'm just going to get that. I have it open in a tab already, so I'll just refresh that. So we start from scratch. So over here, select 12 words and then press generate, and you get what it does is it picks from a dictionary, right? In this case, by default, the English dictionary, 12 words at random, right? Or rather, 11 words at random, and then one of them is the is a sort of a checksum word. So it'll pick those words, and then from this, it'll use the BIP39 spec as well as the BIP44 spec, and the links for that are in the tutorial for further reading, and use that to generate any number of accounts, right? Accounts consist of a private key and a public key, as well as an account, right, or address. So so that's what this is for, and we will actually do that in a later step. But for now, we're just, all we need to do is copy this, right? So I'm going to use a phrase that I prepared earlier on, right, over here, and those will be my seed phrase words, right? Okay, finally, we need to get the Hedera testnet RPC URL. So when we want to communicate with the network, right, and any EVM network, we need to be able to speak to it on a communications protocol called JSON RPC, and there needs to be a server that runs JSON RPC. So I provided links to 2 different options, right? And you can pick whichever you prefer, right? The first one is Archaea, which is a managed service, meaning you just create an account on a website, and then it'll give you a URL with an API key, something that looks similar to this, right? Just copy that and you have to paste it into here, right? And this tutorial that I've linked over here, it will, take you through the steps and guide you through the process of doing all of that. We won't go through that in this workshop, right? But just something for you to follow along. Now, the other option, this is slightly more involved, is that you run your own RPC relay server over here. So you can see this thing that I've got running here is an instance of Hedera JSON RPC relay, and you can see basically it's a server that's running on my own computer, so on localhost essentially, right? The steps to set it up are a bit more involved, right? Because you've got to do a git clone at the beginning. Now, the following steps are quite, you've already done them, right? Since you already have an operator account. And then once you've got that, right, you'll just need to do a few npm commands and then start it, right? And that's pretty much it, right? And then you'll have something like this running in the background, right? And you can just leave it on. The main thing is that by default, if you don't change the config files, right, the URL, the RPC URL will be on localhost, and that's what I'm going to use. So localhost, and if I'm not mistaken, the 7546 is the port number, the default port number for RPC URL. If you use RPC relay, right? So I've used that. If you use Archaea, then your RPC URL is going to look something similar to this over here. So that's your choice. You can pick whichever you prefer, and then let's move on, right? So the next thing that we're going to do, right, is we've already got the seed phrase, and we've got our operator account configured. Our operator account has been funded with HBAR, testnet HBAR, which is the currency of the Hedera network. And so what we're going to do is we're going to create a bunch of accounts that are EVM accounts on the Hedera network so that we can work with smart contracts using those accounts, right? Now, these accounts do not exist yet, right? We need to create them and we need to fund them. So that's what we're going to do next. So we'll need to open a file under the intro folder called generate EVM accounts, right? And while we're waiting for that, let's do an npm install in the background. Right, so that will churn in the background. It will be installing a bunch of packages. So you can see over here, it's installing .env, which is a basic npm package that just reads these environment variables in and exposes them within our code. under process.env. And then we've also got the hashgraph SDK, which is basically the JavaScript SDK that is used to interact with the Hedera network. And then you've also got one of the sub-libraries within ethers.js as well, right? And we'll see that in action within the script. All right, so npm install has completed. That's great. Let's move on to this, right? So once we've got the seed phrase, right, the next step is to fund several EVM accounts, right? So this script has already been prepared for you, so there's really not much to do here, right, except for setting some values, right? So let's say we want to generate 4 different accounts and fund them. We want each account to start off with 100 hbar, and we want to use a derivation path, right? This specific derivation path. Right. Every network has its own derivation path, and the one that I've used here, right, starting with 4460, that is the one that corresponds to Ethereum, not Hedera. And the reason that I've done that is for sort of backward compatibility with Ethereum tools that tend to hard code their derivation path as opposed to allowing configurable on the network. For example, MetaMask, right? It doesn't allow you to set a different one. So if you want to use the same set of accounts with the same set of with the same seed phrase between MetaMask and your development, this is the path that I'm going. So anyway, we've got this configuration done, right? And let's skip ahead to the part where stuff actually happens. Let's make this a little bit bigger. Right. So what this does is it iterates over, from 0 to 3, so that you get 4 accounts, and then it appends a slash with an index of /1, sorry, /0, /1, /2, /3, right, to the derivation path, and then from that it generates different accounts, right, using this bit here. This is from ethers.js. Right, it generates different sets of private keys based on the derivation path and the seed phrase according to the bit 39 and bit 44 spec. Right, so let's go ahead and run that. The node /generate EVM accounts.js. I'll run that and we'll see its output. Right, so the first thing that happens for each one is it works out what its derivation path is. So you can see they're all identical except for the index at the end. So that's 0, 1, 2, and 3, right? And from that, plus the seed phrase, which stays the same across all of the accounts that you're generating, right? You get a private key, you get a public key, and then you get an EVM address, right? So just imagine this beginning with 0x, that's your EVM address, right? So now we've got 4 accounts, and at this point, these accounts, like when we've reached this point in the output, these accounts may not even exist yet, right? So these are just keys, a set of private keys and public keys and addresses that exist locally on your computer, and the Hedera network is unaware of them, right? What happens next is this bit over here, right? We have a transfer transaction in which the operator account, right, is decremented by, in this case, right, 4 and 100, so that works out to -400, right? So its balance is decreased by 400, and then subsequently, right, for each of the accounts that you're generating, right, that gets a hbar transfer of that particular address and that particular amount of 100. So it is -400 for the operator account, plus 100 for account 0, plus 100 account 2, plus 100 account 3, and plus 100 hbar for account index 4, right? So that's essentially it. So -400 and plus 400 in total. So that's essentially the requirement. And then that transaction is executed, and that's what this transfer transaction over here is. Now, we could just take, I guess it's a word for it, but it's always good to, on a network, verify what actually happened. So let's go and do that. Let's fire up hashscan, right? So got that here. So hashscan.io right, is the Network Explorer, where you can see transactions, accounts, etc. on the Hedera network. If it's your first time using it, you might need to click on that drop down here and select testnet, right? Okay, so once you're on Hashcan and you're looking at testnet, which you can check over here or here, right? Paste in the transaction ID that you just copied and hit enter, right? It's important that you see that this is marked as success, right? Meaning that the transfer has indeed completed. And what we'll see over here is that you have your operator account, right? Which you'll notice actually matches the operator account here, right? That you've configured, right? Has transferred approximately 400. That's how much its balance has been decreased. And then each of the recipient accounts, right, is going to receive 100 HBAR each, right? Now, this tiny fractional amount of HBAR that you see over here, right, that's not actually part of the transfer that we populated, right? This is actually a network fee for processing the transaction, and that's being sent to basically the network for the cost of computing that transaction and preserving the state, right? Okay, so now at this point, you definitely have these 4 accounts, and you can check over here. Like, for example, this is an account, the first one in the list, and it exists. The hashcan says, if it doesn't exist, if the step didn't work, then this will give you an error. But this one clearly exists. Now, in my case, because I've used this specific seed phrase and derivation path combination before, this account existed prior to me doing this. But if you're doing it for the first time with your own seed phrase, then what's going to happen is that you'll only see one transaction in which the account was created at this point in time, right? And of course, you'll only see a balance of 100, not this fairly large amount, because I've done this step multiple times by now. All right, so I think that's the very quick recap of the setup or the prerequisites for this workshop, and then we can go on to the actual tutorial part, which starts off with writing the Solidity smart contract. But before we do that, I just wanted to briefly highlight, right, a couple of different concepts of that are present within addresses and accounts on Hedera, right? So Hedera has a native account format, right, which is based on ED 25519, right? This sort of address, right? And that's native to Hedera. Now, Hedera added EVM compatibility, right, subsequently, and now it supports 2 types of accounts in terms of like which kind of keys that you can use. So it also supports ECDSA accounts now, and these ECDSA accounts basically are EVM compatible, and basically they use the same kind of public key, private keys that Ethereum network uses, and coincidentally the same type that Bitcoin uses, right? Now, what you'll see here is that this type of account, it has an account ID, but it doesn't have an account address or an EVM address. Whereas this kind of account has an account ID, but it also has an EVM address, right? And that's critical because to interact with Hedera services, and I know my colleague who has given the previous workshop has covered all the different types of Hedera services, right? You can interact with all the Hedera services using ED25519, and specific to Hedera smart contract service, right? If you need an account that has an address that is visible within the smart contract, then you have to use this kind of account, right? And so that's the reason, right, that we have an operator account, but we also went through the additional step of creating a BIP39 seed phrase and then subsequently generating several EVM accounts from it. And that's the reason why we had to go through this entire step, right? And there'll be more about this in the tutorial, but essentially there is there's a Hedera native account ID, there's also the EVM address alias, there's also an account num alias, and there's also a key alias. So there are like 4 different types of formats. That's a bit confusing, I guess, but that's, one of the consequences of having supporting multiple types of accounts within the same network. But in this tutorial, it's not going to be that complicated. We only really need to think about it in a very simple way. Operator account, use account ID. And for the EVM accounts, use the EVM address. Very straightforward for this tutorial. Okay. Right. Now, as promised, let's finally get started. So we've finished our configuration steps over here. We've got everything here. We can close this .env file and we can open up our Solidity file, right? And now we're starting the next step within this tutorial. So yeah, let's begin, right? So firstly, let's start off with some very basic stuff, comments, right? So a double slash means it's a comment and everything on the rest of the line is a comment. If you want a multi-line comment or, a delimited comment, I should say more accurately, if it's /star, then the rest of it's a comment until it encounters the next // right? Anything in between it is considered to be a comment. So that can span multiple lines if you want to. All right. Now, then the first line on a Solidity file is almost always going to be this thing, license identifier. This essentially specifies a short name or identifier for each license type. So in this case, mine's MIT, and that corresponds to whatever this list defines as being MIT. So you don't have to include the full license. This is considered to be the or something like that. It is not a compiler error if you include it, but it is a compiler. So best practice just to put it inside there. All right. The next thing is to specify the Solidity version number, right? And we do that using a pragma, right? So what I'll do here is I'll type Solidity. So we're saying, okay, we want a specific Solidity number, and I'm going to use 0.817. And what this essentially does is it says only the Solidity compiler with this specific version is allowed to compile the smart contract. Now, the specification does allow for different sorts of ways of specifying. For example, you can use anything that is within semantic versioning or Semver package in NPM, right? So, for example, you can say 0.8 point anything, or you can specify ranges, etc. But in this case, we're just going to stick to one specific version and leave it as that. Now, by way of orientation, right, I'll point this out again with how the tutorials work, right? So let's scroll down to the step that we're at the moment for you following along, right? So in the tutorial, you'll see heading numbers. Some of them look like heading titles, I should say, right? Some of them look like this: step followed by an identifier, a colon, and then some text, right? And that is meant to correspond to this, right? So you'll find a to-do, right? And then you'll find the text that matches this text over here. And then subsequently, you'll say step identify in the accompanying tutorial, and then that number will match this one over here, right? So that's just by way of orientation. In case you're following along, this is how I'd like how the tutorial has been designed to make it easy for you to follow along when you're reading through it. All right, so let's move on. Right, so we specified the Solidity version number. The next thing we want to do is specify the name of the smart contract, right? Now, the way we do that is we use a keyword called contract. And then after that, we specify the name of the smart contract. In this case, I'm going to call it Troubadour. Right, and that's it, right? So anything between this squiggly bracket and its corresponding closing squiggly bracket, that's all considered part of this specific smart contract. So any state that's within it, any variables that are within it, et cetera, these are all considered to be part of the smart contract. Kind of similar, right? But not exactly, like a class within the object-oriented paradigm, right? It helps to think of it that way. Now, let's start with some state, right? So we'll create a primitive state variable, and a good way to start with that is a number. So this type, uint256, right? That's the type, right? And then we'll come back to these later, and then we'll have a name for it, right? So that's called min fee, right? A minimum fee, right? And then we assign a value immediately of 100, right? Because it's a primitive value, we can assign the value just like that, right? Now, coming back to this, public and constant, they are modifiers, if you will, on this particular state variable. What public basically says is that the value of this particular state variable is accessible outside of the contract. So anyone can query its value and find out what its value is, right? And the smart contract actually intentionally exposes its value. Now, the next thing is constant. This means that this value is not really a state variable, but rather it is state and it just doesn't change. It's constant, right? Moving on, let's move on to a dynamic state variable, right? So a very common one that you'll see in a lot of Solidity smart contracts is something called a mapping. It's kind of analogous to a hash map, right? So let's create a mapping, right, called amounts. So what we want to do is store a specific value or a numeric value per address, which is essentially per account that we want to track. So we're tracking a number per account. Now, in a mapping, you have a key value pair, right? So the key in this case is address. We want to be able to see which address corresponds to which amount, right? The delimiter between the key and the value types is this symbol equals an arrow, and then you 256. Sorry. Right, and that's it really, right? So this effectively means that if you look up a particular address, then you can get a value that happens to be a number, an unsigned integer, right? And the name of that is called amounts, right? And we will make use of this later on in our implementation of the functions. All right, so now the next thing is we will talk about some functions, right? So let's take a look at this function over here, total burn, right? So just by way of orientation, keyword for function, name of the function, parentheses to denote a parameter list, and then you've got squiggly brackets, open and close, and in between you have the implementation. So based on that, it's pretty similar to the function syntax that you're familiar with, or you may be familiar with when working with JavaScript, right? So we're not going to say highlight that kind of syntax again. Instead, we'll focus on what the differences are between Solidity and JavaScript in terms of function syntax, right? And the first thing that I'd like to cover is function modifiers, right? So we saw public earlier on, right? And that means something that is visible from the outside or accessible from the outside. And that applies, to state variables as well, right? And functions can also be public. In fact, many of them are. So let's specify public for this one, right? We want this burn function to be public. And we also want it to be something called payable. Now, this is sort of Solidity specific, or I should say EVM specific, saying when we call a smart contract with a transaction, you can send any amount of value with it, right? And that value will be denominated in the native currency of the network, which happens to be HBAR in the case of Hedera, right? So if this smart contract is deployed to Hedera testnet, then if you have testnet HBAR, you can send it along with the transaction. And what will happen is that this function, right, since it belongs to this Trogdor smart contract, that amount of HBAR that you send in with it gets added to the balance of the Trogdor smart contract, right? So Trogdor's balance will go up, right? A smart contract has an address, and therefore you can send it value just like anything else. Now, the difference is that if you want to call a function and send it a payable amount, right, what happens is that function has to opt in to it, meaning saying, oh, okay, I accept a payment via this payable via this payable modifier, right? If it doesn't have it, then the smart contract will reject the transaction, and if the transaction fails, then the value never gets added to this particular smart contract. That's how it works, right? So yeah, that's definitely something that's very Solidity or EVM specific. All right, and let's also do the same thing for total burn, right? So this one is different, right? This particular function does, as you can see from the comments over here, does a bunch of things that do update the state of the smart contract or the network, right? So that's fine. But this function is intended to be called as a form of a query, right? It just returns some value, a value. So because of that, right, what we want to do is we actually want to get rid of, we want to sort of specify that it is, that it doesn't update the state of the network. And the way to specify that is by saying it's a view, right? So the view modifier says, okay, I'm declaring as the function, I declare that I will not update the state of the network. And if you include any commands inside of the function body that potentially modify the state of the network or of the smart contract, the compiler will just reject and refuse to compile. So there's a compile time check for that. All right. So view. The other thing that we'll do is something called external, right? So this is essentially the same as public when it comes to a function, right? Almost the same as public, right? The key difference is that a public function can be called by the smart contract itself and by other smart contracts or accounts, but an external function cannot be called within the smart contract itself. It can only be called by another account or another smart contract, right? So that's essentially what it does. So there are a few different modifiers for you to explore. There's private, protected, external, and public, right? So there's quite a few of them, 4 of them to be specific. All right, sorry, public, private, internal, and external. Those are the 4 ones. Now, moving on, let's specify a return value. Now, this function over here, right, burn-init, modifies state and doesn't have a return value, right? Doesn't need one. This one over here specifically does need a return value, right? So we want to return a balance, right? And any balance on any account of smart contract is always a of type UN256 because that's how it's defined in the network. So this is the syntax, right? So we say returns and then in parentheses a list of types for whatever's being returned. So in this case, we're only returning 1 value, so that's great. Note that unlike JavaScript and possibly several other languages, Solidity does not restrict you to only returning a single item. You can return multiple values from a single function. That's allowed. All right. Now, let's move on to special values that are accessible within a function, right? So when you're in a function, right, typically you can, like, let's say you're doing something in JavaScript, right? You can access anything that's inside the parameter list of the function. And you can also, if that function is within a class, it can access the member variables of that particular class, right? So in this case, you'd be able to access min, fee, and amount as well, right? However, in smart contracts, right, functions also have access to like some sort of network state kind of things, right? And so these comes from things like the block, the transaction, and several other things, right? So 2 of the important ones are called message.sender and message.value, right? So message.sender essentially is a way for a smart contract function to know which address was responsible or which account was responsible for invoking that particular smart contract function, right, at that particular time, right? And the message.value is applicable in the case of payable, where it knows how much hbar, in this case, was sent into the smart contract. All right, so with that introduction out of the way, we're ready to do the first condition, right? So require is a built-in function within Solidity language specification itself that essentially throws an error and therefore cancels, reverts the transaction from that function invocation, unless a specific condition is met. So in this case, we're going to set a condition that message.sender is not equal to address 0. Now, this is a common check in a require statement, checking that it's not possible to use a null address, right? Because this address is a sort of a special case. We don't specifically need it in this thing. We just wanted to sort of demonstrate how to do that, right? So let's interpret what happens, right? So if this function gets called, if this condition is satisfied, the function execution is allowed to go to the next step and the next step, right? But if this function condition is not met, so this evaluates to false, what happens is this message is this text here, 0 address not allowed, is the error message, and then it reverts the entire transaction. So any state changes that may have happened up until this point in time, as part of the execution, they just get thrown out the window, and it's as if this transaction never happened, right? So that's essentially what a require statement does. So now we're going to do the same thing, right, with another condition, right? Message.value, right? So this is essentially the amount of H-bar that's sent in, needs to be more than or equal to the minimum fee, which is a constant value of 100, right? So the smallest unit in Hedera networks is a tiny bar, which is like 10 to the power of, I believe, -8. Essentially, 10 to the power -8 of a full H bar. So you need that 100, at least 100 tiny bars in order for this to succeed, right? This requires statement to allow the function execution to proceed, right? So let's use that and say pay at least minimum fee. Now, I'll make a sort of comment here that this is a common pattern in smart contract functions, where they start off with a set of require statements to ensure that the function is being invoked in only a valid way before the actual main thing that the function does is allowed to do. So this sort of pattern of require statements followed by execution statements, which we'll get to shortly, is a pretty common pattern, right? All right. So let's do the actual useful stuff, right? So let's update some state. So here, right, we want to keep track of how much payable amount any specific address has sent into this smart contract, right? So we'll do amounts message.standard, right? Plus message.value. So we're actually making use of this this variable, right? So message.sender is incremented by message.value, and then it's stored back inside of this mapping, right? So that's essentially what this does, right? So each time this function is called and these two require statements do succeed, then we expect the message.sender address, right, whatever its value is, to be incremented by message.value amount, right? Now, the next thing we want to do, this is again another pretty common pattern, is to emit an event when there is a state change that is of interest. So in this case, we want to emit an event, but before we can emit an event, we have to specify that event, right? So let's scroll up here to step 18, and we can find the burnination event over here that's been named, right? So we just need to include the keyword of the event. And then inside of it, we specify the event parameters, or I should say data, right? So these are the fields that the event contains. So basically, who as an address and amount as unsigned integer. That's what we want to emit. So now that we specified the event, we want to emit it, right? So this time we have the same name, Burner Nation, and Burner Nation over here. So let's emit that Burner Nation event, right? And now we need to fill in the values of what, who and amount, right? And I think it might be almost intuitive by now that the who is going to be an address, which is message.sender. And the amount is going to be a unit 256, which is message.value. Quite straightforward, this one, right? All right. So that's it, really. I believe I've covered the entire syntax of the Solidity part of that we've used, at least within the smart contract. Now, this smart contract is extremely simple, right? There's a ton of different items, right, in terms of syntax that we have yet to cover, right? But you know, this is good enough for the purposes of the tutorial. So yeah, let's move on, right? So now, just to wrap up this sort of introduction section of the tutorial, right? Let's like talk a little bit about software libraries and developer tools, right? So in order to interact or develop smart contracts on Hedera Smart Contract Service, which is essentially the EVM offering from Hedera, right? You can do so in multiple ways. Now, this tutorial will cover two different ways of doing it, or two different approaches, I should say. One is to do it like the Hedera native way, and you can interact with the Hedera Smart Contract Service using Hedera SDK JS, right? And that has its own API, right? The other option for you to use is to use something that would be familiar to you if you have experience in working on smart contracts on other EVM compatible networks, for example, Ethereum itself or any of the other networks, right? So for this, you'll need a JavaScript library that is designed to talk to JSON RPC APIs, and also has other functions, for example, like the one you saw earlier on, where you take a seed phrase, a bit39 seed phrase, and turn that into a set of accounts, all that sort of thing, right? You need a software library to do that. The popular ones are Ethers.js and Web3.js. And in this workshop, we will be using, among those two, we will be using Ethers.js. Now, the next thing is Solidity, right? A Solidity compiler, right? Now, if you use something like Hardhat, that tool will manage Solidity for you, and you will see that in action later on in this tutorial. Alternatively, you can also use the Solidity compiler directly. There are multiple tools that have that available.
Brendan,
I think you're
you are
mute.
on mute.
Sorry about that. Okay, so yeah, in this tutorial, we'll be using the Solidity compiler directly, and we'll also use Hardhat's managed version or equivalent of the Solidity compiler as well, right? Now, I'll point out that in order to write EVM compatible smart contracts, Solidity is not the only option. There's also another option, several other options, in fact, the most popular of which is Viper, but we're not going to cover that today, right? Today's this tutorial is going to be all about Solidity. All right, and finally, in order to work with smart contract development, there are several sort of development frameworks. We've got the popular ones are Truffle, Hardhat, and Foundry, right? And these provide utilities, script structure, documentation, etc., that are very useful in development. And And yeah, in this one, we obviously are not going to cover all of them, but we will cover we will just work with Hardhat and keep it simple that way. But essentially, this tutorial is structured in such that we cover like 2 different development pathways to work with smart contracts. One is the Hedera native way, where we use the Hedera SDK in order to work with it. And then the other pathway is to use Hardhat, which is more of the EVM tooling that you might be used to working with from, say, other networks, right? So with that out of the way, right, that's the end of the introduction, and let's begin. Let's begin working. We'll start with the Hedera SDK for JavaScript. So if you're following along with the tutorials, then what you'll need to do is go back to the docs folder and navigate to this one over here and follow along. Right, so this is what we'll be doing here. Now, back to the repo. Right, so the Hedera network offers multiple services: smart contract service, file service, token service, and consensus service. And each service has several different ways that you can interact with it, right? But these interactions are like, as they are exposed, they are actually something called HAPIs or Hedera APIs, and working with them is very low level and definitely beyond the scope of this tutorial, right? So instead of interacting with it at such a low level, right, Hedera provides a set of SDKs in different languages. The one that we'll be using today is the JavaScript version of that SDK, right? And we will use that SDK to essentially work with the Hedera Smart Contract Service, or HSCS. All right, so the first thing we want to do is let's go into the terminal, go out of the intro folder and go into the Hedera SDK JS folder, and then let's do an npm install. Right, and wait for that to finish. The first thing that we're going to do once that is installed is to actually compile the smart contract, right? So this smart contract that we've written here, we actually haven't done anything with it, right? Like, we've just written it as a text file, and it isn't actually doing anything, so to speak. And now we're going to start using it for the first time. So by way of intro, you can see the trogdor.sol file here. And now in the Hedera SDK JS, right, we've got some files prepared here, right? But you can see the smart contract that we have is empty, right? And I've also left in almost empty files here for expected outputs from the smart contract compilation. But these are basically an invalid ABI, invalid binary file, and an empty smart contract. So that's our starting point, right? And we also have several scripts which we will be completing later on. So the first thing we want to do is we want to actually have this smart contract, and we're not going to write it from scratch, right? Instead, we're going to just do a copy from the intro, right, to Hedera SDK JS /trog, and then you want to copy it to this folder, right? So now, if we open up this file over here, right, we can see that in Hedera SDK JS, this file here exists, right? Same content as what we had in the intro. And that's what we wanted, right? Okay, that's the first step, copying smart contract. Now, the next thing is that we need the Solidity compiler. So npm install, right? Okay, there are several ways to install the Solidity compiler. I think the one that I find the easiest is the npm route, but you can check out the documentation from Solidity lang to find several others. All right, so I already had this version of Solidity installed, but it'll be a bit slower if you're doing it for the first time. Now, note that the binary that it installs is not the same as the package name, right? That's Solidity, that's Solidity JS, right? Apart from that, there's no, that's just the main thing that you need to be aware of, right? Now, if you issue a command to output its version, right, you can see over here, right? That's the version number, the specific git commit, if you wanted to find it on the Solidity GitHub repo. And importantly, right, this bit here tells you that it's been cross-compiled. So this is not the original Salty, but rather the version of it that's been cross-compiled using Unscripten and therefore converted into JavaScript. And that allows us to install it in the way that we have, and it's a bit more convenient to work with using tools such as Truffle Hardhat, which we will happen to use later on. All right, so okay, we have got a version of the Solidity compiler, right? So now let's just see what it can do, right? So this is a fairly simple tool in terms of the interface that it exposes, right? The number of flags and options actually fits into a single screen terminal, which is not the case in most Unix tools, but yeah, this one's pretty cool. So a lot of options here, but the ones that we're really going to be using are these two, right? Bin and ABI, right? We want to output the EVM bytecode, and we also want to output the ABI as a JSON file, right? So these two are the ones that we'll be using. Right, so now these two files, let's just remove them actually. Right, you don't have to, but I'll just do it just for the sake of demonstration. Right, so those are the ABI and bin files that I have from my previous usage of the compiler that I've just deleted. And so what we want to do next is to actually run the compiler. So now we're moment of truth. Was our smart contract valid? Did we write valid Solidity syntax? So bin ABI, and so this file that we have here is trogdor.sol, and we're going to compile it, and we're instructing it to output both the EVM bytecode and the ABI JSON. Right, and now to ls, right, we can see that these files have been generated again, right? So let's take a look at them, right? So the bytecode, right, is this basically massive long string of hexadecimal text. Nothing much to really read into this, really, because it's literally not meant to be human readable. Just the most important thing to check really is that the output has indeed been created. Now the next thing, right, is that the ABI output is the next thing of interest, I should say, is the ABI output. Now this one here is actually valuable. Now it outputs it in this like very dense format that's kind of hard to read. So if you happen to have the JQ tool, I recommend that you do this installed. And if you're on Mac, you can just install this via brew, or if you're on Linux via apt-get, I believe. So trogdor.sol.abi. So it really is a JSON file. So then you can get this, syntax highlighted, parsed version of the JSON file, and you can see how this actually corresponds to the file, right? Quite easily. For example, you can see that it has a burnination event, and the parameters are an address and a uint of 56, for example. You can see that it has a payable function called burninate, and it has no parameters, and it has no return value, right? Total burn has no inputs, but it does have a return value of type uint256, etc. Right? So this ABI does give us a pretty good idea about what the smart contract is, right? And what its exposed interface is, I should say, and is definitely intended to be human readable. Right. All right. So we have just successfully compiled our smart contract, and that's like step one. So step two, I should say, is to deploy the smart contract, and then step three, we can interact with the smart contracts, and that's the sequence that we'll be going through. So let's open up the deploy smart contract file over here, right? So we've got this file that's been pre-prepared for you, just like we did with the Solidity file, and you can use the same sort of steps to interact with it. to follow along with the tutorial using the step ID identifiers over here, right? So the first thing we want to do is to initialize the operator account, right? And to do that, right, we have and to do many of the other interactions here, we've imported the Hedera SDK for JavaScript, right? And this is a required statement, and here are the I would say classes or objects that help us do what we want, right? So the first thing we're going to do is create an account ID. String, and then we want process .env dot operator ID, right? And let's just quickly sort of understand how that actually happens, right? So this file here, right, .env reads in the .env file that's in the root folder of this, like one level up, right? So then that's reading in operator ID, and the .env library sets that and under the environment variable called, and that's why it's accessible under process.env, right? So that's what's going on, right? And then we'll use the same sort of thing, but this time we will initialize a private key with a different environment variable, right? From string. And then we'll also get process.env operator key, right? Okay, we've read those two in, and then after that, initialize the client with a default testnet configuration, and then set the operator account as being what we just initialized using those environment variables. So subsequently, we can use this client to issue all of the network interactions, right? And that's what we'll be doing, right, in the subsequent steps. So, okay, so the next thing is we need to read in the bytecode file, right? So this file over here, right? Oops. The API, I want the bin, right? So this code here is what we want to send onto the Hedera network and use this to create a smart contract, right? The ABI is just for us to know how to interact with it, and that stays in the client side. This, the binary file, the EVM bytecode, the one that we cannot read, that's the one that actually goes onto the network. All right, so EVM bytecode, what do we want to do here? We want to read the thing from disk, so it will be fs.read file. And then we need to specify the name of the file. So let's get that. All right. Then the next thing we want to do, right? We can't, using the SDK, the Hedera SDK, we are not able to directly deploy that with a deployment transaction. There's actually a step, a prerequisite step, which is that we put it onto the Hedera file system first, and then subsequently we say, hey, Hedera smart contract service, check out this file on Hedera file service. Okay, go and deploy that. So that's essentially what the sequence that we're going to go through now. So file create, we're going to do file create transaction, right? And this is essentially a Hedera file service API, right? And then we're going to do set contents, right? So the file create transaction contains basically the binary file that we just read in. Then once we prepared the transaction, we actually need to, put that onto the network and check that the network has executed it, right? So file create dot execute, and then file create transaction dot get receipt, right? So once a transaction has been executed, we have to wait for it to complete, and then we get a receipt for that transaction, which contains the detailed information about the transaction and its completion, right? Vitally, right, what we're interested in the receipt is this this property called file ID, right? Because we need to use that subsequently when we are telling Hedera smart contract service about what to deploy, right? So now we are going to reference the bytecode that's been stored on the EVM bytecode that's been stored on Hedera file system using that file ID, right? So for this, we're going to need a contract create transaction, right? And then we're going to say that where the bytecode is located. So set bytecode file ID and then specify the file ID. And then we're going to say set gas, right? So you have to pay for the transaction using some amount of hbar, and that should cover it, right? Okay, next up we have a deployment transaction. So smart contract deployment dot execute, right? So we prepared that transaction here, but it hasn't been sent to the network. This actually sends it to the network, and just like before, we are going to get the receipt, right? And the receipt will contain the contract ID, which we are then going to output into the console. Okay, I think we're ready to run that. So node deploy smart contract, and let's run that script. Wait for it to do its thing. All right, so we can see here HFS file create transaction. Here's a transaction receipt that has been output, right? And we do indeed have a file ID, right? This object over here, right? Then subsequently, Hedera smart contract service contract create transaction, and we have its transaction receipt, and we have its contract ID, which is this object, and then parse that and output it as a string. All right, so we could just take its word for it that this has worked, but let's not do that and go to hashscan and verify it on that that's actually live in Ledger. So again, hashscan.io, check that you're on testnet, and then put that, copy that, right, from the output, paste it over here, and you should get to a contract page. Now, if you see a page that says not found or something to that effect, it basically means that the deployment transaction did not succeed. So definitely you do want to check that. All right. So what do we want to do here, right? So we get a contract page, and I think the one interesting thing here is that you see that it has an EVM address. Now you'll notice something like a little bit strange or funny. In EVM addresses, you're not used to seeing like a whole bunch of zeros preceding a number at the end, right? In Hedera, this happens, and it happens when you deploy a smart contract via the SDK and calling the contract create transaction directly. Now, if you do it in a different way, right, via the Hedera smart contract service directly, and we'll see that in a subsequent step when we're using Hardhat and Ethers.js, you'll get a different type of address. So in Hedera, we refer to this as an EVM address, but specifically we call this the long zero EVM address, right, as opposed to a non-long zero EVM address. Right, and then the other thing that you'll see is contract bytecode, right? So you'll see a whole bunch of hexadecimal text, right? Note that, right, this is not the same as, you know, the bytecode that was output previously, right? So if we ls and then the bin file, right? So this bytecode is quite similar to, but not the same as this, right? Because this bytecode, when it is deployed, it is sent to the network, and then the network has to process this, and then whatever the outcome of the processing is, it gets output, it gets stored on the network. So not exactly the same, right? In case you happen to check that, right? But it is deterministic, right? This bytecode will always result in this bytecode. And I won't get into the details of why that's necessary or how that works, etc. That's beyond the scope of this tutorial. All right, interacting with smart contracts, the thing we want to do next. So we've already got a contract that's been deployed, right? How do we actually do stuff with it, right? So the key here is that we have this smart contract, right? And we have its ABI, right? So we know what the smart contract does. And importantly, right, we also have We also have from the API, we know its function name. So we know that we can call a burn init function. We also know that we can call a total burn function, right? This one updates state, this one doesn't update state. And also, because both of these are public, right, both of these variables, the Solidity compiler automatically generates accessor functions for them. So you can actually query amounts, and you can also query min fee if you want to. All right, so to do that, let's use another file that has been prepared earlier on called interact with the smart contract. Interact SC, right? So this same pattern as before has been prepared, and we just need to complete a few critical steps that I want to highlight, right? So the first thing we want to do, right, is to go right to the bottom, right, in step F1 and copy the contract ID that we had earlier on. So copy that and paste it over here. So essentially, we're telling this this script that we want to interact with this specific contract that we just deployed. You can give it any other contract ID if you want, as long as it effectively has the same API. It should technically work. All right. So moving on, we've got the next step where we initialize the operator account. Now I'm going to be a little bit lazy here and just copy paste. Right. And that should do it. Right. So now we've got the operator account initialized, and then the next line we're going to do is we're going to actually interact with it. Now, let's see. Right, so we're going to invoke the payable function, right? And we're intentionally going to do it with a 0 value just to trip up the require function, because we can see the implementation over here, right? We know that if we call this function and the value is 0 or anything less than 100 really, right, it'll just reject the transaction because and revert it, I should say, because of this, and we're basically trying to trigger that and make that happen, right, on purpose. So so what do we do here? So because this particular function is public payable, right? We're going to do this where we do a contract execute transaction, right? And then we set contract ID. And then we set gas. Pay for the transaction, right? This contract ID is the one that we passed in over here and was obtained from the deployment step that we just completed earlier on, right? And finally, we set function, right? And this is essentially identifying that the function name is burn init. It doesn't take in any function parameters, so that's just fine as it is, empty. And then finally, we need to execute it, right? And then this will do a try and a catch in case of an error. So in this case, we're expecting it to catch and output an error, right? Now, the next thing is we're going to do it like sort of properly, right? So we know that we're going to send in a value of 123, which is more than 100, the minimum required for the min fee, and therefore that require statement should pass, right? So we've got a contract execute transaction. We're going to do the same thing, set contract ID, and then we're going to do set gas, same as before. The only thing that's new is that we're going to do a set payable amount, right? And here we'll specify 123. But we don't want to send in 123 H bar. We want to send in 123 tiny bar, right? So H bar unit dot tiny bar, right? So note that the numbers here, right, like numbers here for anything that's sent in by payable and message of value, is denominated in tiny bar, not in H bar. So that's how we get that here, right? And then set function. And again, we're going to call burninate and with no parameters, and then we want to execute it. All right, so we've got essentially contract execute transaction happening twice with the exact same thing in both cases. The only difference is that set payable amount is 0 by virtue of it not being even called here, and here it's got a value that should satisfy the requirement. Now, the next thing that we're going to do is invoke the view function with no parameters, a view function with no parameters, and that one is the total burnt function, right? So that's external view, if I remember correctly. So since this one is a view function and it doesn't update state, we don't want contract execute. We want contract call query, right? Yeah. So set contract ID, set gas, and then set total burnt, and it also doesn't require any parameters. And then we need to do set query. All right, let's do execute. And note that you do have to pay for queries on the Hedera network. So it's not just transactions that need to be paid for that change state. All right. Okay, so this code here will actually run the query, right? And then in this case, we have a return value that we need to process. Now, in the smart contract, right, we can take a look at total burn, and its return value is of type UN256. The contract call query doesn't necessarily know that, so we just have to specify that we are going to extract get UN256 from it. All right. Now, the next thing we're going to do is we're going to invoke the amounts function, right? So recall that amounts is a mapping, and since it's public, the Solidity compiler has automatically generated an accessor function for it. Now, this accessor function, right, requires input parameter of type address, and then its return value will be UN256, right? So that's that's what we're going to be querying next. But in order to do that, we need an address, right? And at this point in time, right, we don't have the address in this script. At least we don't have the address of the account we want to use. So so let's do that, right? So what we need to do is derive its address from the private key. Derive the public key from its private key, and then from its public key, we can obtain the EVM address. So let's do that. So operator private key dot public key. Oops. Let's just check that operator private key exists. All right, operator key is over here. Operator key dot public key, and you get operator public key. Operator EVM address dot public key is dot to EVM address. All right, awesome. All right, now we have the value that we can use as an input parameter for to invoke amounts, right? So now again, we're going to do another invocation of contract call query, right? contract call query. And then we'll set the contract ID to ID, set gas, set function. Right, and now there's something new, which is we need to specify a parameter, right, or an input parameter for this function. So let's go ahead and do add address. And then finally, we can do set query payment. All right, we're ready to execute it. So at this point, this will call the amounts function, and then we're going to pass the return value, which happens to be uint 256. So get uint 256. All right. That's it, right? So let's run the script. I think we're ready to run the script. So /, no, / interact with smart contract. All right, so a lot of output here. Let's go through them one at a time. Oh, receipt status error, contract execute transaction. I was not expecting that. So what was the very first one? Okay, so this is indeed contract revert executed, and the reason for it is because we didn't send in a message value, right? So that's fine. Sorry, threw myself off there. All right, contract execute transaction number 2, right? To the transaction receipt. This one looks successful, right? Now, here's the interesting thing, right? Now we interact with the contract itself for number 1, which is for total burn, and that returns a value, right, of 123, which is what we expected. Now, if you run this multiple times, this value will increase, right, by multiples of 123. And then again, now we're calling the amounts, and we also have a return value of 123. All right, I'm going to take a short break, and I will come back in a couple of minutes. All right, see you in a bit. All right, I was trying to see if I could get the background noise to come down a bit. Hopefully it's slightly better now than it was just now. Anyway, getting back into this, right? Let's run the script a second time and see what the values are, right? right? And this time, right, when we do the contract function results, we're expecting it to be more, right? 120 times 2, which is exactly what we've got, right? Yeah, so that's that's basically it, right? We've deployed, after deploying smart contracts, we have sent some transactions to modify its state, and then after that we queried state, and we're getting the values that we expected. All right, and we also demonstrated a rejected transfer as well. This one over here, the first attempt to modify the smart contract state was essentially rejected because we ran into this require statement within the burn function saying, hey, you're not allowed to do it unless you hit this minimum threshold. Okay, so again, right, we could just trust the output from what you see on the terminal, or you could verify it, right? So what I'd like to do here is to actually get a contract, the contract ID, which I have over here, right? And search for that inside of hashgraph. All right. And you should get to a URL that looks something like this, and it should be a contract page, right? Now, once you have this, right, you can scroll down to a section called recent contract faults, and you should see something like this. Let's see. Yeah. So sometimes if the page has been open for a while, right, to save sort of bandwidth, if you will, it'll have this like pause and play button. So make sure that you unpause it essentially. Yeah. And then when you get down here, you can see your contract fault history, right? So this one here would have been the least recent one, I should say, right, would have been the deployment. And then subsequently, this would have been the first attempt to call it with the payable function, the burn function with the value of 0. And then you can see here the error message. And then the second one where it succeeded. Yeah. And then I ran the script 2 times, right? So the second time it did this, right? So again, error for pay at least minimum fee, and then subsequently a success, right? So there we go, right? So click on the row for like the failed transaction and navigate to its transaction page, right? So this one, right? So you should see a transaction contract revert executed, right? And then if you see the scroll down to contract result, you see this pay at least a minimum fee, right? And you can get more details over here if you want, right? Now let's go back to the main page and go to the most recent call, which would have been a successful one, right? And you can see over here a few different things, right? So one of the things is transfers. You'll see that this account has decremented an amount of HBAR, right? And it has, gone to as a transfer to this other account, right? And this other account happens to be the smart contract. This is the operator account that has been interacting with it, right? So my operator account has essentially transferred some money into this smart contract. All right. The other thing is you'll notice within trogdor.sol, right, the Solidity file, that it's been emitting this burnination events, right? Now, let's scroll down a bit here and take a look at logs, right? And you should see a single entry in the logs, right? The address is the address of the smart contract, and the index field is 0, right? Since there's only a single event. The topic essentially is a hash of the signature of the thing. So signature of the event, I should say. So burnination address uint, right? You take that and you hash it, and you get the topic, right? And it's a bit more complex than that, but that's the rough idea. And the data is essentially what's in it. So it should contain an address followed by a uint 256. And you can see here, right? And this is going to be pretty low level, right? You can see here the first half of it in terms of width, right? All the way up until that 4474. So I'll make this a bit bigger so it's easier to see, right? Let's see if I can get it to align nicely. No, that didn't work. Okay, so if you go from here all the way up until here, right? There's a bunch of padded zeros, but if you start from here to here, that's the address, right? Of my account. And then if you go from here up until here, that gives you a unit 256. And if you convert 0x7b into decimal, you should get 123 because that was the amount, right? So let's just do that. Convert 0x7b to decimal, right? 123, right? What's it called? Smart contract verification. And one of the things that that means is that the page can have an ABI attached to it. And if it has an ABI attached to it, it'll be able to parse, for example, event logs. It can actually should be able to display to you that this event was a burn donation, and the data can say, okay, the address was this, and that was that, and you wouldn't have to like look at the raw hexadecimal values yourself. All right, so yeah, that's it for the Hedera SDK section of this tutorial. And in the final half an hour, I think we can go over the Hardhat and Ether's way of going through it. So if you've been following along in the tutorials, going to back to the GitHub repo, right? Just go in the docs folder, move over to Hardhat, right? All right, so Hardhat is a development framework specific or helpful for smart contract development. So very common stack among developers in even compatible networks, and you can use it with minimal effort or configuration with the Hedera network as well, right? So let's move on to setting up the project, right? So let's go to the folder for this, Hardhat, right, within the repo, and then npm install. You get the prerequisites, right? Now let's close all of this and open up Hardhat, right? So this is the Hardhat project, right? And we have a config file, right? And we also have a package.json file, which we don't need to open. And we also have a contracts file. Now this contracts file has got nothing in it, right? So we're going to initialize that shortly, just after we finish installing stuff. Now this has a bit more to install than previously because it has to install .env. It also has to install Hardhat itself, plus a couple of other, Hardhat related packages. So that will take much longer than the previous npm installation. So we'll just wait for that to churn through. Or maybe while we're waiting for that, we can actually copy the Trogdor Solidity file into here, right? So where's that intro? Copy, and then over here, paste. Right, so now we've got a copy and we've got the original. Let's trash the original and rename this. All right. And it looks like the npm installation has succeeded. All right. So now we've got the completed smart contract inside of here. Let's switch over to hardhat.config.js and just like sort of quickly go over what's inside of it, right? So what this does very critically is it needs an RPC URL, right? So that's where it's going to connect to this, and that's reading it, right, from the .env file in the root of this folder that we set up right at the beginning, right? It also needs a seed phrase, right, which we also set up at the beginning, right? And it's going to use a derivation path plus the seed phrase, configure that to generate up to 10 accounts. I think that's the default, but if we need more, we can create more, but essentially right now, out of these 10, only the first 4 really do exist. Within Hardhat, you can configure what version Solidity you use. It's vital that needs to be matching, that needs to match with the pragma that you specify inside of the files. So here we're going to use 0.8.17. All right. Next thing here is that we have to specify different networks. So Hardhat always comes with a default set network configuration. So this is not a true network, so to speak. It's a emulated or simulated network that runs completely in memory, right? So it just basically is a fake, but it's very useful for testing because it doesn't require network hops. It doesn't require like transactions happen instantly, et cetera, right? Which is useful when you're testing, right? But then here is an instance of a real network. So that's the one that we'll be using, called Hedera testnet, right? And that uses the configuration for the accounts via the seed phrase, and it also uses the URL that we configured for the RPC that connects to this earlier on, right? So that's a brief sort of whirlwind tour of the Hardhat config file that has already been set up for you, right? Nothing really to do here, right? And we've already copied the smart contract while we're waiting for the npm install. Now let's check out a feature of Hardhat called a REPL, REPL, which stands for read evaluate. Now this shell that I've been using here, right, is ZSH. That ships by default with Mac, and that is a form of REPL. But you can have like tool or library or environment specific REPLs, and that's what Hardhat provides. Hardhat's REPL is specific to connecting to a EVM compatible network and interacting with it through RPCs predominantly, or through other APIs that Hardhat exposes. Right, so that's what Hardhat's REPL is designed for. And in order to connect to it, what we're going to do is npx Hardhat, which will run the Hardhat version that has just been npm installed, since it's present in the local directory. And then the subcommand is console, which is what it calls its REPL. And then we specify which network that we want to connect to, right? So your choices are essentially what's been specified inside the config. You can either use Hardhat or Hedera testnet, and I'm going to use Hedera testnet, obviously, right? So this actually will connect to the Hedera testnet network, and you can see, you'll see that in the background, this thing will start churning through some output as and when I interact with it, right? So you'll also notice that previously, when I was using the shell, right, this was its prompt, right? That's what its prompt looked like. Now my prompt is this instead, right? And this is one of the things that sort of signal that you're within the REPL. All right, and you can do .exit to exit it at any point in time, but we're just going to be into it, right? All right, so the first thing we're going to do is basically test that the network works, right? And we're going to get a block number. Now, Hedera doesn't, strictly speaking, have block numbers. It just has block numbers as a form of RPC compatibility thing, but it's still a good way to sort of check like whether we are live and getting the latest information from the network, right? It's kind of like a hello world when it comes to connecting to a EVM compatible network. So the syntax for this is slightly complex. Hopefully I get it all right. So await require, and then inside of it you want to call Hardhat. So this is basically the same as, I guess when you do it with npm installed, right? And then once we've got Hardhat, we do .network .provider .send, and then this basically allows us to send an RPC, and the RPC that we need is each get block by number. And then we want to send it some parameters of latest, I think. And if I get this wrong, I'll just copy paste it. The syntax is quite different to get exactly right. Yeah. And then we await this RPC response, right? Once we've got it, then we're only interested in the number value of it. Interesting. I'm just going to copy paste it then. Let's see if that works. All right. Yeah. So I obviously had a syntax error when typing it out manually. All right. So let's copy this number over here. And where are we? Trying to find my there you go. Window. All right. So convert. Yes. We get that. All right. Let's go to the Hedera hashgraph, right? And where are the latest blocks? There we go. You can see over here, the latest block is 773,2000, and we've got 773,2000, right? So there we go. You can see it's kind of live now. We'll repeat that command again, right? And convert that again. You'll notice that. Oops. Did I copy that right? No. Let's do it one more time, right? And that's 052. And you can see 052 is here. So, there's one block approximately every 2 seconds. So you can see that it's increasing, and the number that we're getting when we query the RPC value over here is sort of following along in tandem with hashgraph. So that's good. Awesome. Right. So the next thing that we want to do is to check the address, right, that we'll be using. So this one doesn't actually interact with the RPC at all. It's a far simpler one. So we want to do await hre.users.get signers. And then we want to get the first one, and then we want to get address. Did I do a typo? There we go. So that is 0x07ff, right? Which is what we expected. It's the same one that we generated earlier on when we ran our generate EVM account script, right? Yeah. So you'll notice that this is not the same as an operator account, right? So the address of my operator account was 0x7394 something, right? And this is 0x07ff, right? And the difference is the operator account was the Hedera native account that we obtained from the Hedera portal, whereas this one is one of the EVM addresses that are generated using seed phrase, right? So yeah. So let's actually run this a few times, right? But we will just change the property, right? 1, right? And 2, and 3, right? And each time we get a different set of addresses, and these are the ones that are all generated from the seed phrases, right? All right, so we've finished basically like doing our hello world for the REPL. We checked that we are indeed connected to the Hedera testnet network, and validated some data on it. So let's exit the REPL, right? Now, the address that we've been using by default is this, right? So let's just check that on hashscan, right? So let's just go to hashscan.io, and then under testnet, search for that address, and we can see that this address has been funded, right? We're on our account page. We see the same EVM address. We see that it has a balance of HBAR, and this verifies that the account exists. Now, if you do the same steps and this says, account doesn't exist or something to that effect, or if you come here and there's no balance, it's 0, then you will not be able to proceed with the rest of this tutorial. So you need to go back to previous steps and walk through them again. right? So now we're going to do the same sequence: compile, deploy, interact, right? But this time we'll be using Hardhat and Ethers.js instead. That's going to be a bit simpler. npx hardhat compile. Now, what that does is it grabs. Oh, why did it say nothing to compile? Maybe I've done it earlier on. So let's go and delete the cache, delete the artifacts. Right. All right. Now let's tell it to compile again. I think it must have auto-compiled earlier. Okay, now it's just compiled one Solidity file directly, and it's recreated the cache and artifacts, which is what I wanted to see. All right. So firstly, let's take a look at the build cache, right? Which is in the cache and Solidity files cache.json. So you'll see here there's some output, basically saying a bunch of things that we expect, what the name of the smart contract is, what the version of Solidity is, et cetera, right? The next thing is that if we open up the let's see, contracts, and then we see trogdor.json, right? We can find, okay, we've got its API over here, right? And we've got its bytecode over here, right? So this bytecode over here will be the output from the Solidity compiler, and this bytecode over here will be the output that we expect to see on hashgraph. What actually exists on network after this bytecode has been processed, right? And a more detailed explanation of that is available in the tutorial. Now, previously, right, in the Hedera SDK version of deployment, we use a contract create transaction. Now, Hardhat, Ethers.js, etc., all the EVM tooling do not understand HAPIs at all, right? So it's not possible to do a contract create transaction. Instead, what we'll be doing is something called an Ethereum transaction, which basically is defined in one of the HIPs, HIP Hedera Improvement Proposal number 410. Go and check the full details of that. The link is provided in the tutorial. But essentially, every single transaction that is created via an EVM compatible tool is an Ethereum transaction, right? And that Ethereum transaction basically is a wrapper around how EVM compatible networks encode their transaction, right? So we will be deploying a transaction, right? But we'll be doing it in not only through a different tool, but also the underlying protocol level way that the contract is deployed is completely different as well, right? End result is the same. We'll still have a deployed contract, with the exception of the EVM address not being a long zero address like we saw earlier on, right? Okay, let's see that in action. So let's again go back to the console, right? So npx hardhat console, connect to the Hedera testnet network. Okay, and we're in, right? Now, what we're going to do is repeat the command that we did earlier on for getting the signers, right? So, but this time we're going to assign it to a variable. Deployer is equal to await hre dot equals dot get signers, I believe. Get signer. There we go. Then close that, then 0. Oops. Okay, so this will provide us with a signer with address object, and that's what we wanted. And then we need to create a contract factory, which is a step before the deployment. It's specific to Ethers.js. So let's just create trogdor factory. Wait. hre dot get contract factory, and then we just need to refer to it by its name, right? Typo there with a capital letter and another typo. Pardon me. All right, that worked, right? So how did that work, right? We didn't specify an ABI or an address or whatever. That's essentially because of the way Hardhat manages the compilation output, and we took a look at it earlier on in the artifacts and cache directory, right? So that's how it knew to find the relevant binary and the ABI and generate this contract object, right? As we see over here. A contract factory object, right? And from which we can use to create instances of a contract, in other words, deploy them, right? Right, so that one's pretty simple. So we can just say trogdor, right? So that's the actual contract itself. Trogdor is equal to await trogdor factory dot. And we can see that sets off a set of RPC activity over here in the RPC relay server that I've got running. And this will take a few seconds because deployment is a transaction and it's a fairly heavy one to process as well. But that's been completed, and now we have a contract, right? So this is the value of trogdor now. All right. So what should we do next, right? We need to get a trogdor deployment, right? So let's just do that. It is equal to await trogdor deploy transaction and that's fairly instantaneous. It did have to make a network hop, but because the deployment had already completed, we got the results back pretty quick, right? And what we want is trogdor deployment dot contract address. Essentially this property, right? This is what we're after. So now we're going to go over to hashscan, right? And search for that contract address, and we should find it, right? So this is the address it was deployed to, AB3F, and we've got it over here, AB3F. It's excellent. And we've got our contract bytecode. We only have one transaction on it, and that would have been the deployment transaction, right? So now let's interact with it. We're going to do the same set of interactions that we did before, but this time we're going to do it within the REPL instead of writing a script to interact with it. So we'll get more instantaneous feedback. Await trogdor dot functions dot min fee, and that should return us 100, right? Basically. Now let's do the same thing again, but instead of min fee, we want total burnt. Right, and that gives us a value 0 because we have yet to interact with it with any account, right? So now let's call the burninate function. So await trogdor dot functions dot burninate. Okay, so this function has no parameters, but in ethers.js, you can specify the way the API to specify it is an object at the end where we can specify things such as the payable value, right? So value of 1, 2, 3, right? So that, right, would be how you expect to send it in. However, what we actually need to do is we need to multiply this by 10 billion, right? And the reason for this, let me just make sure that I get the right number of zeros, right? It's because previously, right? So inside of the SDK JS tutorial, when we set the payable amount, it was just 123 tiny bars, right? And the SDK understands that natively. Now, when we go through the RPC, we're going through an EVM compatible layer, right? And when we do that, right, we actually need to convert between tiny bar and something called waybar because it implicitly assumes, RPC implicitly assumes because of the EVM specification, that the number of the tiniest unit is 10 to the power of minus 18, whereas a tiny bar is 10 to the power of minus 8, right? So that's where the 10 billion comes in, right? So you've got to multiply it by 10 billion or divide it by 10 billion, depending on whether you've got the sending request or receiving the response, right? And full explanation for that is included in the tutorial text. So anyway, let's issue that command, right? And we'll send it a burn name. And we'll wait for that to churn. All right, it looks like it has completed the transaction, right? And let's press play over here. We should see an additional transaction. Let's click on that, and we can see that burn has indeed happened, and the smart contract has been sent 123 tiny bars. Great, right? And yeah, just like before, we can see the logs as well, and we can see 123 in hexadecimal plus the address that it was sent from, 0x07ff, as we expect. All right, that's great. So what do we want to do next, right? So now we want to query min fee again. And we expect that to be the same because it's a constant. And we also want to query total burn. So instead of seeing 0, like we did the first time, this time we will get 123. Right? Now let's also call, let's see, amounts, right? So in order to do that, we need to get account on the EVM address is equal to, let's see, await hre dot there's dot get finance address. That should do it. A typo? Yes, it was a typo, right? So this is my account one EVM address. Now, yeah. So now if I call amounts on it, right, I should get a value of 0. Okay. Yes, there we go. So let's change that to amounts, and then I will send in account one EVM address, and that should give me a value of 0. Now, if I get account 0 EVM address, let's just do that, right, which is the one that, oh, what am I doing? I have sort of stuffed up this record. Account one EVM address was what I used earlier on. Account 0 this time, right? Sorry, dot address. Right. So now I have an address, and now I'm going to invoke this with account 0 EVM address, and that's the one that I've been calling it with, and I expect to see 123 this time, which is what I get, right? So I've interacted with it, called burn-in-8, and then I've also called total burnt as well as amounts and got the value of 123 with this specific account. Now, that's it basically. Now if we press play here, we won't see any more transactions because we actually haven't changed the state of the network. The last few things I've done have been interactions. Okay, I believe that's it for the interactive part of the workshop, right? So now just by means of to sort of conclude this workshop in the last couple of minutes, right? Congratulations, right? What we have covered is a few things, right? We've been able to write the code for smart contracts using Solidity. We've been able to compile the Solidity code into EVM bytecode. We've been able to deploy that code, that EVM bytecode, onto Hedera smart contract service. And we've also been able to interact with the smart contract on Hedera smart contract service to query its state and to also change its state. Now, the bigger picture of this is that we've been able to do it in 2 different ways, right? We've been able to do it using the Hedera SDK, so using its native Hedera APIs. And we've also been able to do it using EVM toolchains, specifically Hardhat and Hedera JS. We've also learned about how to use the Yeah, we've also been able to learn about like the Hedera network more generally, how it works. We've also been using hashscan quite extensively to check the on-state changes and how it's been like how our actions in our code and the command line, how that impacts what happens in the network. And yeah, I think we've covered quite a lot of ground in the basics of interacting with smart contracts on the Hedera network, right? So if you've been like kind of confused, what is this whole Trogdor and Burninate thing? The link to that is in the tutorial text in the outro, so please go check it out. It's a fun little video and game that comes along with it. So anyway, back to the tutorial. Where do we go from here? Right, Solidity is a fairly simple language, in my opinion. Right, it's a high-level programming language with a fairly compact syntax, and we've covered the essentials, like the bare essentials. There's a lot more to cover that hasn't been covered here. Right, constructor, functions with parameters, structs, logic like iterative, conditional. Function modifiers, working between one contract and another, like instantiation, interfaces, external libraries, etc., etc. Like there's a lot of stuff that we haven't covered here, and in real world you wouldn't ever really work with a contract that's as simple as the Trogdor one that we use in this example, right? So to go further, I encourage you on this regard, I would encourage you to use the Solidity language documentation. So that's on docs.soliditylang.org. Link is provided in the description. And the other thing that I'll point out is that there is a difference, fundamental difference between Web 2 and Web 3 development because of smart contracts, right? And that is to do with testing, right? I would strongly encourage that you check out this Hardhat testing tutorial over here to cover the basics. That is something that I really wanted to cover as part of the smart contract workshop, but didn't really get around to because we're covering a lot of ground in a very short period of time. So it's extremely important to test code in general, but in Web3 with smart contracts, because the code is immutable, you kind of have to get the logic correctly tested and verified earlier on in the development lifecycle. That's on the shift left, if you're interested. So go check that out as well. Right. I think I'll wrap that up over here. One of the things I mentioned in the tutorial with hashscan is that it doesn't have smart contract verification. So you can't see the code of the smart contract that has been deployed, even if it's your own one, and even if you wanted it to be visible. And when you look at the interactions, you can't necessarily understand what is going on without like delving into low-level stuff. So smart contract verification is something that the engineering teams are working on, and hopefully we will have that out for you soon, right? Still a work in progress at this point in time. So on that note, I will wrap up, and if you have any questions, comments, etc., if you want to take a look at this in more detail, I strongly encourage you to check out this repo, right? And I will paste the link to that in the chat, right? So, all right, that's it. Rico or Adash, do you want to wrap up?
Yeah, sure, Brendan. I'm just gonna quickly drop the link into the chat once more because I think you have posted it in the host and panelists section. So I just put it in the general section for everyone to access it. And I'm just gonna give people like a few seconds to drop their questions in the Q&A if they have any, or else we're gonna wrap this up. And for the people who have joined us here today, don't worry if you have missed the initial part of the webinar. We're going to send you the recording over email very soon, so you can access the entire recording once more. Or if you want to go over a few things again, well, you can just view the recording that we sent you. So I don't see any questions in the Q&A section or the chat section, so I guess we can call it a day. Thanks a lot, Brendan, for conducting this session, because I'm pretty sure that people have learned a lot from this session, and there's a lot more people who are gonna benefit from this session once they view the recording. And thank you for joining us today. For those of you who has joined us, because I know it's pretty late in the night or early in the morning for you guys. So thanks a lot for joining in. And once again, thanks, Brendan, for conducting this session. Have a nice day.
Awesome. All right. Ciao, everyone. Bye.
Bye bye.